Thank you very much for coming to my session. My name is Brandon Brown. I'm a 3D printing application engineer here at Markforged Systems. Some of you might have seen the clip of me riding my bike in the general session, but today we're actually going to be talking about designing strong end-use parts for the Markforged CFR process, actually by examining a case study of some 3D printed mountain bike pedals that I designed and printed using this process. So it should be really interesting. Shouldn't just be going over some process facts. We should have some interesting content in there. With that being said, I'm actually going to launch a poll really fast to see who of you are using 3D printing in this audience. There should be an option for Markforged users as well. So go ahead and answer that when you get a chance. Let that roll. While we have that poll open, I'm actually going to say too, if you have any questions during this session, our moderator, Jesse, is going to be answering them. You're going to be able to put those in the Q&A tab. You should be dropping a question in here any moment now. And then I'll also be answering some questions live in the live at the end of the presentation. Looks like we got some poll responses here. I'm going to be ending the Looks like there's a lot of, we've got some Markforged users in here, about 30% of you. That's pretty cool. If you're not using Markforged, go ahead and put what you're using in the chat. I always like to see what the people using 3D printing but not using Markforged are using. Oh, wow, we got one guy running his X7 right now. That's pretty cool. So with that being said, there will also be some handouts for this session. I'm going to be covering a lot of content specifically that's in the design guide for Markforged, this process. So make sure to check out the session details and documents and links section under there, under the presentation, below the screen. That'll show you where those are. Really useful content in there, especially if you want to like keep some of this for later. And with that being said, I'm gonna put my webcam off and tell you a little bit about me. I joined Markforged Systems back in September of 2020 when we were acquired from Quest Integration. I had a very similar role at Quest Integration. I was an employee there for 5 years, a little over 5 years before the merger. I have a Bachelor's of Science in Mechanical Engineering from Montana State University. I graduated in 2017. For those of you doing math in the audience right now, I interned at Quest for 2 years when I was in college. I have over 20 certifications with Markforged, HP, SolidWorks, and a few other 3D printing companies. And outside of work, as you could probably tell by the content of this presentation, I'm a pretty avid outdoor enthusiast. I really like to mountain bike and ski and just get out in general. So a little bit about what we're going to be covering in this presentation. We're first going to go through a little bit of a project introduction. I'm going to introduce the case study we're going to be using here. I'm going to talk a little bit about the Markforged CFR process for those of you that aren't as familiar with Markforged. And then I'm going to talk a little bit about design for additive manufacturing principles we're going to need to keep in mind, and the design of the part we're actually going to be using as a case study. We're going to talk about design for CFR, or continuous fiber reinforcement, and the associated principles and techniques for reinforcement design, as well as the actual reinforcement design for this part. And then we're going to go over the results. One more thing I wanted to mention as well, speaking of CFR, thank you to Markforged for sponsoring this presentation. If you're interested in learning a little more about Markforged after this presentation as well, make sure to stop by the booth in the expo section or reach out to learn more. And before we get started as well, I always like to establish some conventions. So the first thing is when I'm referring to the XY plane, I'm always going to be referring to the plane that is parallel to the print bed. And then the build direction is always going to be perpendicular to the print bed or the XY plane. And that's going to be referred to as maybe the Z direction in some instances. And while this is defined a couple different ways, for the sake of this presentation, because this is how Markforged does it, as do a lot of other companies, we're going to be defining the overhang angle as the angle between the print bed and the reference surface. So now let's get into the project introduction. I'm actually going to launch a poll right now to see how many of you ride bikes in this audience, just to get a lay of the land. But modern mountain bikes, as you probably already know, are more capable than ever. They use designers of these machines use advanced materials and innovative design practices to really maximize performance and reduce mass. I'm going to end the poll here really fast to see who we got. We got a lot of a lot of riders in the audience here, checking the chat to see. See, we also have some have some more Markforged users and some actually a Bobcat in the chat. That's pretty cool. Go Cats. So yeah. And then as many of you, though, that do ride, which is a lot of you in the audience that answered the poll, these are very, very, very customizable products. Most riders customize their bikes heavily for better fit and function. And something that's very, very personal is pedal preference. A lot of riders, for example, really like clipless pedals or pedals that ironically have clips on them. And a lot of riders, including myself, like flat pedals. So I, having, kind of bigger than average feet and, kind of being choosy with this in general and having a background in mechanical engineering, wanted to create something very personalizable for my feet. It needed to be lightweight, reversible, so double-sided, customizable, so I could, really kind of contour it to my feet and actually maybe even give this to other riders. Needed to be very durable, obviously. I'm going to be riding mountain bikes on it, so it's going to kind of get beat up pretty bad. It needed to use off-the-shelf hardware. I didn't want to spend my time, kind of acquiring custom hardware or really having to go into detail sourcing that stuff. And then it needed to be serviceable. I didn't want to have to throw it away every time I, needed to change a bearing or, needed to replace a part on the pedal. So naturally, being that this is a custom product or something I'm doing custom kind of at lower volumes, 3D printing is a great fit. Mainly because 3D printing is really accessible and fast. We have a couple machines in our shop and it's pretty accessible even to, the average consumer these days. There's no additional cost for part complexity or customization of every part or print. All you really need to do is change the file and the setup is really about the same and they can produce complex geometry relatively easily. But in the past, strength and accuracy, like part accuracy, have been a real big concern for 3D printing. But this really isn't the case with Markforged CFR process. And this is really why I decided to choose this process to make these pedals, because there are advanced high performance materials like carbon fiber and carbon fiber reinforced nylon materials available. And it produces really precise, beautiful parts because of the use of this material, advanced software, and very high quality hardware. So what about this process? How does it work? So how this process works in general, I'm sure many of you have seen this, an FFF 3D printer in the past. So they use a thermoplastic filament that is pushed through a heated nozzle, and that actually extrudes filament. It extrudes plastic, and that is basically deposited in the shape of each layer on top of the previous layer until you have a part. However, where Markforged CFR really differs is not only in the use of advanced materials, but a second print nozzle that actually can print fiber materials. We're going to go over what materials it can print a little later in this presentation in more detail. But really what happens is that fiber is extruded through a second nozzle. It's heated up because it's got a plastic sleeve around it, and it's ironed down into the polymer matrix or the plastic where it bonds. And this matrix gives the fibers protection and structure because obviously they're kind of hard to structure without some sort of plastic matrix. This is what you see in other composites. And then these fibers provide increased strength and act over the cross section in the structure provided by the matrix material. This process is capable of producing really, really strong, useful parts, a lot of in-use parts. A lot of times you see this in applications like shop tools, so like machining fixtures, soft jaws, welding fixtures, end effectors, a lot of shop tools and other manufacturing applications like that. But it's also great for high-strength prototypes and end-use parts like that tail wheel arm you see there on the kind of top middle. That's an application I was involved with, and it's actually a functional aircraft part, which is really, really exciting. So what about the equipment that that uses this technology? So there are two main machines, and I've included a handout for the machine spec sheets if you want to get more into the details of each of these machines. We'll also be able to talk later if you're interested in learning more. But it's namely the Mark II, which is the desktop series top of the line CFR machine, and the X7, which is the industrial series CFR machine that both can print all of the materials, except you do have some more material choices on the X7, namely for more regulated applications, and we'll get into that a little later. And then in addition to the other material choices with the X7, you do get a larger build volume. You get a laser micrometer on the print head for assisted bed leveling, adaptive printing, and actually blacksmith inspection functionality. And my actually my moderator is going to be doing a presentation on that later today. You should definitely check that out if you're interested in learning more. Has motor encoders for more accuracy, a webcam, 50 micron layer height, turbo print for faster printing, and some additional materials like we said before, namely for more regulated applications. So that being said, now that we have actually know a little more about the process, we need to start creating a CAD file for our model or design. And I'm going to share some of the considerations for this process that we need to take into account while doing this, because like any manufacturing process, while additive manufacturing can, and CFR can produce very complex geometry, it does have some unique limitations. If you see in the handout section, so session details and in the session details and like documents and links, there is a design guide in there with most of this information. So we're only going to kind of skim through this for general concepts. So the first thing you need to keep in mind is your print orientation. You need to choose this ahead of time, at least as early in the design process as possible. And while you're doing this, you want to, because this is going to drive a lot of your design features, you need to make sure you want to try and maximize bed contact if possible. In general, this will drive a few of the other things below this. It'll help keep forces and stresses, depending on how you design the part, in the XY plane. That's a really important consideration. So you don't want to be, as we'll talk about a little later, pulling the layers apart because the material is weaker in that direction. You want to try and keep critical features and dimensions in the XY plane as well, because the printer is more accurate in the XY plane, because that is the plane in which the nozzle is being positioned. And then in general, you also want to try and avoid as much overhangs and support material as possible with the orientation you choose, although there are some modifications that you can implement to help correct this. Speaking of support material, try and avoid it. Once you have once you have an orientation, and again, you're going to have to balance some of these things depending on the application and the needs. Try and keep the overhangs in your part when you're designing it or choosing an orientation above 40 to 45 degrees from the print bed. I say personally about 45, that's kind of the magic number. Obviously above if you can. This is called using self-supporting geometry, and this really helps eliminate support material use like you can see in this example and reduce these overhangs. It just in general helps with the part. It also has the benefit, so a few other benefits, but mostly just removes sacrificial material and then thereby helps reduce print time and post-processing time. If you have holes in your part, especially if they're not functional holes, if they don't need to be round, you can use a teardrop or a diamond shape hole, for example, for fluid channels or like bolt head clearance holes. These are both great options. Try and round your corners. So rounding corners, as you know, very similar to like if you are familiar with like FEA analysis, sharp corners are stress risers, and by rounding them off, this reduces warping and stress concentrations that are associated with these sharp corners. But a little known benefit is this actually results in faster print times. You don't have to suddenly slow the print head down and then change direction all of a sudden. It can round that corner at a higher speed, and you'll actually see some noticeably faster print times in some situations. This is also kind of an uncommon one, but try and chamfer the bottom edges of your parts. This reduces, I don't know if those of you that do 3D print, know that first layer tends to swell a little bit. I'll call it elephant's foot or like splaying or warping. This helps reduce or remove that. This typically about a 0.5 millimeter to 1 millimeter at a minimum. And this makes the part easier to remove from the bed as well. If you have to use like on the Markforged process, you have to use a spatula to get it off. So it makes it a lot easier to do that as well. Okay, and then additionally, it's not just avoiding features that are too small, but know the dimensional capabilities of your process. I'm not going to go super into this because it's all in the design guide, and if you're designing parts for this, you'll probably have that open at least the first couple times you do it. But in general, try and make sure your parts A, fit in the build volume if possible, and B, so you don't have to split them up, and B, abide by these minimum constraints. You definitely want to watch that. Same thing goes for fiber. We're going to go over where to place fiber a little more later in this presentation. But if you're planning on placing fiber on a part, especially within a specific area, you need to make sure there is enough room for it. Another thing I always like to bring up, and this is brought up in the design guide as well, is to use inserts for properties that you can't print. A lot of times, customers I see will say, well, we can't print that material, or, hey, we can't get this. We can't print the part. But a lot of times you only need that locally. And you can use, for example, like nuts and heat set inserts, particularly heat set inserts for metal precise threads. You can use metal or plastic inserts for wear surfaces, or like slippery, smooth surfaces, like say Delrin inserts, or like dowel pins for wear surfaces, like you see on that end effector. You can use pins and screws for alignment if you do have to assemble parts together for precise alignment. And then you can use bearings and bushings for smooth concentric surfaces. So you can either press a bearing in, like we're going to be doing in this this example, or if you have an accurate hole, a really accurate hole that you can't print within the accuracy of, you can push like say a drill bushing in, and that gives you the accurate hole you need. It also gives you a better wear surface. And if that hole's printed in the Z direction, it also gives you a slightly stronger hole, and again, a much better surface finish. Also, keep the tolerances and precision capabilities of the process in mind, albeit, the Markforged printers are phenomenally accurate. And sometimes you do see better than this. In general, this is about what you should expect for the desktop and the industrial series. Again, the industrial series is a little more accurate because of the adaptive printing and the introduction of motor encoders. It's also really useful to keep in mind some general diametric clearances. These are in the design guide. And again, you're going to need to do some determination of this for yourself. We're going to talk a little bit about a process for doing that later in this presentation, in this example. But in general, these are a good starting place for these kinds of fits, like a press fit, a close fit, and a free fit. I've found these to be relatively accurate for at least most geometry. One of the biggest ones that you always think about, I don't know if many of you know this, and ever had a part fail when you print a part that's loaded in the Z direction, but avoid loading in that build direction. I have an example here from the Onyx FRA, so one of the matrix materials, directional properties. You're going to notice that the strength in the build direction is dramatically lower than it is in the other directions. And while we can get around this to a large degree with CFR, the tip I'll share with you later, it's really important to try and avoid this if possible. You might have to do some gymnastics to get around this, like split up parts or do a redesign or two, but it's almost always worth doing because parts can fail pretty dramatically in this orientation when printed like this or loaded like this. Speaking of splitting up parts, definitely good to know when to do this. Typically, you're going to have to split up parts if the part cannot be printed efficiently as one part. For example, if you have poor feature, you're kind of juggling between poor feature resolution or too much support or weak portions of the part. There's really no good print orientation, or if the part's too big to be printed in one piece, you can take it and you can split it up into a couple of different parts using screws, pins, glue, and even a really helpful tip, in my opinion, is to use some woodworking joinery in combination with some of these fasteners. To get a good, strong joint between these parts. But typically, there are Markforged customers out there printing parts several times the size of the build volume successfully, splitting parts up like this, especially with the capabilities of CFR. Now that we know the design constraints of our process, we can actually start designing our part. So the first thing I needed to really do before I could start designing was to select some hardware off the shelf that we could use. So the first thing I did, when the most challenging one, is trying to find some bearings and bushings and a spindle that was compatible with standard bicycles. And really, I chose the Crank Brothers hardware, so spindles, bearings, etc. They sell a long spindle kit. This is what I ended up buying because it just kind of had all the parts I needed right off the bat. And then I chose M3 by 16 screws as pins because M3 is a fairly standard pin size. And then put hex nut on the other side of the pedal to retain them. And this will actually play into the structural performance of the pedal as well later. So once I had all the parts, I started opened up SolidWorks and modeled the critical parts up for fitment. Then I started sketching around these parts, and you're going to notice that I can actually change the shape of this sketch, or if I wanted to get really fancy, I could drive this using variables to customize the size and shape of this to my foot or someone else's foot, because everything is driven off of this sketch, as you're going to see. Once it was done, I actually extruded the pedal and started to add some other design features. For example, I added a hole and used a sketch-driven pattern based on the shape, added some lightning cuts, and then ended up rounding all the surfaces, again, to decrease the chances of warping and increase print speed, and added some more lightning cuts as well and threads for the dust cap and chamfers on the top and bottom. If we look at a cross-section of this pedal, you can see how the bearing and the bushing both press fit in, and there's clearance for the spindle, as well as threads for the dust cap. And typically you don't want to print threads, but these aren't really loaded threads in this case, and they're not super critical. It just kind of keeps dust out and kind of helps retain the bearing. So we could get away with it in this case. They're fairly large threads as well. Typically wouldn't recommend this, but there are some things we did to help mitigate chances of failure with this pedal as well. Additionally, looking at a cross-section of the pedal, you can see that there's a couple things going on. Those of you that bike will notice, will be familiar with the concept of concavity, but sometimes riders like pedals to be concave or have a kind of a curved shape to them. And while this introduces support material in this orientation, I'm going to be printing it like if you're looking at it sideways like this with the largest surface down for many reasons. This would introduce a lot of support material, not a great surface, etc. So what I ended up doing actually was adjusting the depth of the socket head clearance hole. And what this does is it allows the pin to protrude out of the back of the pedal more or less. And you can actually adjust this to have no concavity, more concavity, less concavity, etc. on the fly. Additionally, you're going to look at the lightning cuts, and they have a I-beam-like profile, and everything's at a 45-degree angle, so there's no real supports needed here, which is really, really nice. Additionally, this concentrates materials under the edge and under the hex nuts, and this is going to come into play a little later in the design. So now that we have the basic CAD design done, it's time for the second part of the process, and that is reinforcing with CFR, designing our fiber layout in Eiger. So why use fiber at all, though? Typically the materials we're going to be using, as we're going to talk about, they're all, nylon-based materials. There are a lot of nylon pedals. Why use fiber? Well, first of all, fiber makes parts stiffer, stronger, and more durable. So that's immediately attractive. But in reality, you can really use it to optimize a part's strength profile and therefore its mass. For example, I don't need to, print this at a high density because the fiber is going to bear a lot of the load, and we can actually leave the inside kind of semi-hollow with the default infill structure. And by using this as well in a lot of industrial applications, you can actually replace a lot of metal parts and get all of the advantages of polymer 3D printing, which is pretty cool if you ask me. So we also now need to choose some materials for this process. We have a couple choices, as you can see here. We have, about 5 matrix materials and 4 fiber materials to choose from. There's a handout as well for the composite data sheet that has a lot more information on this process. Feel free to take a look at that if you're really, really interested in the more of the granular properties of these fibers and matrix materials. But with that being said, I'm going to start talking a little bit about those matrix materials. The base one that the Markforged users are all probably familiar with is Onyx. Onyx is a chopped carbon fiber reinforced nylon that produces really great finishes, accurate prints, and it has pretty great mechanical properties, pretty great general use material. That fiber, in addition to some of the other things Markforged does, really, really helps keep those prints really, really nice and accurate and stable in printing. The next material for applications that where chopped carbon fiber may not be allowed, or where you need a pure nylon, is nylon white. It's exactly what it sounds like. It's a kind of a standard nylon material. It can actually be dyed colors, which is something really cool about it. And then we also have a few other materials that are printable on the industrial series machines, namely Onyx FR, which is a UL94 V0 self-extinguishing material for applications where this is desired. Onyx ESD, which is an ESD safe version of Onyx that actually is kind of targeted towards electronics manufacturing, electronics housings, parts where this is a requirement. And for the X7, Onyx FRA and carbon fiber FRA, which we'll talk about in a little bit, but this is basically Onyx FR and carbon fiber FR that meet FST requirements and have associated certificates of conformity and traceability documentation required for highly regulated industries like the aerospace industry. So let's talk a little bit about the fiber materials now. We have a couple to choose from, namely the first one and the most famous one for those of you that know Markforged is carbon fiber or carbon fiber FRA. for the regulated version. Carbon fiber is very lightweight, it's very strong, and it's very stiff. However, as you might know, especially the cyclist in the crowd, it is expensive and it can be brittle, especially in some loading cases. It's great for applications where you need maximum stiffness and strength and the lowest possible weight. The next one we have, which is a great general purpose reinforcement, is fiberglass. Fiberglass is the least expensive fiber that Markforged offers. It has moderate strength and stiffness, and it's very sturdy, albeit it's heavy. So this is great for a lot of applications that, they need to be strong, but you can afford some extra mass. Think a lot of shop tools, like those soft jaws we saw earlier, are a great example of this. High strength, high temperature fiberglass is essentially a stiffer and stronger version of fiberglass with higher heat resistance and a lot higher impact strength. The heat deflection temperature of high strength, high temperature fiberglass with an onyx matrix is roughly 150 degrees Celsius. However, it is heavy like fiberglass and it's a bit slower to print. Great for higher temperature applications or something between fiberglass and carbon fiber, because it still is cheaper than carbon fiber. A good example of this being used in an application would be the welding fixture we saw earlier, or thermoset molds, thermoset epoxy molds. Those are another really good application of HSHT composites. And then lastly, we have one of my favorite fibers, just because it's so unique, is Kevlar. So Kevlar is extremely impact, abrasion, and fatigue resistant. It's very tough, and it fails in a ductile manner. So it doesn't just snap like some of the other composites do, it'll tear. However, it has less axial compression strength. It is UV sensitive, which isn't as big of a deal because it's kind of closed up in these composites. And it is hygroscopic, so moisture sensitive. So it's great for durable parts, parts that are going to see a lot of abuse or where brittle failure is undesirable, and in applications with a lot of cyclical or impact loading. Those end effectors you saw earlier from Dixon Valve are a great application of Kevlar. So I'm actually going to launch a poll really fast and ask you which fiber you think I should use. I'll leave this open for a second. Leave it open for a few more seconds here. I'm going to leave this running. Make sure to get your answers in because I'm about to close it. A lot of people think Kevlar. That's a really interesting one that I didn't expect. I will actually go ahead here and I won't reveal what material I used yet, but some of you might be guessing what I ended up using. But before we talk about what material I use, I'm going to talk about where to place fiber. In general, you want to try and place fiber where the highest stresses are expected in the part. And with the software that we have, we can do this fairly easily. And you can use different fiber fill types and schemes to optimize the strength profile of the part that you are printing. Something that's rather unique about this process. You don't have to have a solely homogeneous material, as you'll be able to see in the images and the demonstration we're going to do. So the first thing, I'm going to go over some of the two fill options that we can have for this process. You can actually select two fill options per layer, like in each layer of the part or each group of layers when you select them. And those are concentric and isotropic. The first one, being concentric, just puts fiber around the walls of the part. You can select the number of rings, so the default's 2, or you can put it around the outside, the inside, or both walls. And you can control this layer by layer, but this is largely done in groups or kind of put in the middle. There's a lot more information about this in the design guide as well. The other one here we have is isotropic fiber. So it uses concentric fiber around the walls at default settings, even though you can still adjust the number of rings around those walls, and then fills the rest of the layer with a fiber in a specified direction. By default, what it'll do is it'll actually alternate to form a layup. So when you select a group of layers, which is what you'll typically do in Eiger, which you'll see here shortly, it'll actually go through and it'll change the direction of this fill from 0 to 45 degrees to 90 degrees to 135 degrees to get basically alternate the angle 45 degrees every layer to get strength in every direction. Although you can customize the direction based on either layer by layer to your content, or you can actually change the alternation scheme, the layup scheme, if you want to. So how do you actually use this though? It's great that you can do both of those things, but how do you actually implement this fiber? The first one, and these are also in the design guide as well, at least most of them are, is pretty basic. It's sandwich panels. It's like you think of like an I-beam where you have the most material, except in this case, it's the stiffest material. So the biggest equivalent cross-section of the matrix material, if you're going to analyze it that way, on the edges of the part. This can either be placed on the extremes of the bending axis with isotropic fiber, if that's on the top and the bottom of the part relative to the print bed, or on the sides of the part with concentric fiber, if it's you know, on the vertical walls of the part relative to the print bed. And this is great for resisting one-dimensional bending or bending in one direction. But what if you need a little more strength? So this is where striping comes in. And striping is basically just sandwich panels with additional fiber reinforcement panels between the two extremes, either concentrated towards the edges of the part near the sandwich panels, or more commonly, evenly strewn throughout the part. This provides additional bending both in the primary direction, the first direction we talked about previously, and in the second direction. They almost act like stiffening ribs, and it adds significant torsional resistance to the parts for very, very little extra fiber. There's actually a new function in Eiger that does this for you for a cross section. If you selected the whole part and it was fairly uniform like this, you could actually set it up and have it auto stripe it for you, which I think is a really neat feature. But what if you need even more strength? And striping's not really cutting it. You could actually do something called shelling, which is putting fiber on all walls of the part. Those sample break levers you've seen from Markforged, if you've seen them before, are a great example of this. This is kind of the best for overall strength because there's fiber under every wall of the part. There's concentric around all the vertical walls and isotropic at the top and the bottom. It effectively resists all loading cases pretty well. If you need more than this, though, for much more demanding applications, you're kind of pushing the limits. You can actually combine reinforcement schemes together. So a really common one, especially for that tail wheel arm you saw earlier in this presentation, shelling and striping together. So adds a bit more strength. So not only do you get some more bending resistance and some more loading resistance, you get a lot more torsional resistance as well. It was really important in that application. And this really further strengthens the part with, again, a little extra fiber addition. If you really have to, you can fulfill these parts with fiber. It's generally not super recommended because unless it's absolutely necessary, because it adds a lot of print time and cost. The fiber does get costly. And parts are usually often designed around being fully filled. Additionally, the surface finish isn't as good as you would see with the kind of more sparse infill options. So with this fiber, I talked about this earlier. One of the really cool things about this is a little bit of an aside, but you can actually use these fiber reinforcement techniques to prevent delamination of your parts. You can actually bolt through the part to hold the layers together if like peel loading is unavoidable. What happens is if you say put fiber underneath the bolt heads and underneath or around those heat set inserts, whether you're mounting it to something or you're just bolting through the part for this purpose alone, the fiber actually takes those loads that would normally be peeling the part apart, peeling the layers apart, and transfers them to the bolts, which are much, much stronger than the surrounding plastic in the build direction, and results in a part that is much stronger and can be you can generally use to get around those loading conditions. You can't really do this with a lot of other 3D printing, other FDM or FFF like technologies. That fiber reinforcement makes this uniquely possible, at least to a practical degree. And then additional aligning your fiber reinforcement, it's really important to balance the fiber. So when fiber cools, it contracts, and it contracts at a different rate and a little bit differently than the surrounding plastic does. So if there's a large section of fiber, especially about a bending axis, that is not balanced or matched on the other side, like the picture below, then the part might warp. I actually had this happen once on an application. We were making a tombstone for a milling machine, and it threw it off. It wasn't much, but it threw it off enough to have to redo the part. So it's really important, so when you're done, is to add fiber on large sections to counter this once the design is done. It'll also add a little bit of strength. Additionally, make sure your isotropic directions are balanced. So if you have a 0, 45, 90, 135 layup, it's really important that the number of layers are a multiple of the layup directions. So you're not getting, like, say, 3 layers in the 45 direction and 4 layers in the 0 direction if you had a 2-direction layup. That'll also help mitigate this problem as well. Okay, now that we have kind of gone through the CFR process, I am going to actually switch over to Eiger here quickly, and we're going to start reinforcing this part. So this is our pedal, like we saw earlier. The first thing we're going to need to do is I've already imported the file, but we're going to need to actually specify a build direction in Eiger. This is really easy. All you do is just click the face you want facing down. You can manually rotate as well, but this is much, much easier. And now we need to select our materials. So out of the matrix materials, I don't think it makes much sense to have self-extinguishing bike pedals. I don't think that are electronic or electrostatic discharge safe bike pedals. And we want that carbon fiber in there for a better finish and a little more stiffness and strength. So we're going to go with default onyx. And then I'm going to counter to what many of you think. I'm actually ended up choosing carbon fiber for this application because in general, we want this, it's going to be fairly well protected. And while it might not make sense because it is a rather abusive application, we want this to be as light and as stiff as possible. And while the pedals are already kind of on the cusp of being able to survive this alone with just plastic, adding this little bit of carbon fiber adds a lot of stiffness, a lot of strength, and a lot more peace of mind per se. While Kevlar would probably be a fine choice as well, this is what I ended up personally going with to make the pedals as light as possible and really eliminate some of the internal mass, as we'll see, by allowing the infill to persist. We've updated this already, but I actually did by default, it adds 4 layers in the top and 4 layers in the bottom of isotropic carbon fiber. And this actually really helps us. We can change this a little bit, but this number is divided by 2 between the top and bottom layers. This really helps us though, right off the bat. This is what we want. So let's go into the internal view and actually start customizing our fiber layout. As you'll see here, we already have fiber at the top and the bottom of the part. If you look at this bar on the bottom, this is something I always like to describe first. The left side is the bottom of the part. The right side is the top of the part. So as we scroll through this, we can actually see we're scrolling through the part. And this is how we're going to leave it. We actually, if I turn on infill visibility, this actually has a 37% dense triangular infill. And because we're using fiber, we do add a little bit of extra mass and print time for the fiber, but we can remove a lot of material on the inside. We don't have to print this solid or at a higher density because the fiber is taking most of that load at the extremes. I'm going to turn this off for the sake of being able to see some of the other stuff. And then additionally, you can actually see the alternation of the fiber angles when we go through these layers. But the first thing we need to do, and something you'll notice, and I forgot to mention, is the white material is onyx, the blue material is carbon fiber. We need to add some more reinforcement to this. I'm happy with it being at the edges, but I don't know if you've noticed, but the bearing and the bushing kind of intersect, right? So this hole is loaded in the Z direction. I'm worried about splitting here, but you're going to notice that these hex nut cavities actually terminate right at the area where this load is transferred. So what we can do is we can actually put some fiber underneath these hex nut cavities on both sides to not only add some stiffness to the pedal, but generally guard against this whole thing delaminating, kind of just wrapping this all into one. So let me go in, and what I'm going to do is I'm going to actually select where this turns from hex to a circle right there. That's layer 20. I'm going to go in, I'm going to select my group of layers, 4 layers. I'm going to hit create group and then use fiber. And then you can see some of the fiber options we have here, like we can choose concentric fiber or we can use the striping option. We're not going to really use this because this is all the layers we really need. I'm going to do the same thing on the other side here really fast. Okay, layer 123. We're going to do the same thing, grab it, hit create group, then use fiber. And now it's actually done. It'll actually go through and live slice this and update all of our cost and print time metrics. I'm going to go ahead and hit save. And now we are ready to print our pedals. Just like that, easy as that. So now I'm going to go back to our presentation. And before we print it, there's something really important that we need to do. Obviously, you saw these carbon fiber prints can get kind of expensive. So I always like to print some unit tests beforehand. This is essentially like printing a small section of the print beforehand to verify that it fits. So what I do and what I recommend doing, this is in the design guide as well, but is identifying a few critical features of your print. In this case, we had like some screw threads and some press fits that we wanted to kind of peel out. Isolate those critical features, design some segment variations with, say, different clearances, and then print and test them with the same settings and orientation of materials you'd be printing your part with normally. And when we're done, when you're done with that, you can actually update the original model with unit test data. So change the clearances, et cetera, whatever you need to do to make it fit, and then write those results down for later use. Because a lot of the times you're actually going to end up doing a lot of similar parts, for example, and it's really important to have those kind of stored for your machine, your application, et cetera. So this is exactly what I did. I actually designed and printed some unit tests for the bearings and the hardware fit. And then once I was satisfied with some of the fits I had, I adjusted the model and printed some Onyx-only tests to test the ergonomics and the full hardware fit of the pedal against my feet before printing the carbon fiber one like you see here. This is actually a video of it printing on my X7 in our Post Falls office location. These are the actual pedals that I was riding to. I filmed these. I go ahead and actually started assembling these like you see here. And while I get this going here, you'll see I'll hammering the bearing in. It's all the stuff in the kit, putting the screws in, getting it all ready to go. First thing I did, and while I do this, I'm actually going to launch a poll to ask you guys if you guys would ride these pedals. I actually weighed these, and right off the bat, they're pretty similar weight to similar pedals the same size. They're actually a little lighter because they are semi-hollow, and they're made of kind of a lightweight composite. Some of this, and this is a pretty thin pedals they're being compared to too. Some of the pedals, it's a lot lighter than. And then I ended up going ahead and mounting them up on my bike. So I'm going to go ahead now and end the poll. I'm going to give you guys a few more seconds if you hadn't had a chance to get your answers in yet. That's a lot of confidence, guys. All of you that answered the poll said you'd ride these, and that's really encouraging because that's exactly what I did. I actually took these out to nothing too extreme. I'm not one of those crazy mountain bikers like some of the guys at our company that are doing big jumps, but I still like to ride a lot of technical stuff and ride pretty fast. Took these out to a bunch of riding spots in the Spokane, Coeur d'Alene area, like Canfield Mountain, Beacon Hill. I even took it, rode it on my gravel bike and took it to Silver Mountain Bike Park, which is a pretty aggressive gravity park here in the area. And I was not easy on these in the slightest. This is all footage I took while riding these pedals. Not easy on these in the slightest. As you can see here from the pictures, this is on my gravel bike currently. And when I took this picture, but a bunch of the pins are bent. There are sections of the pedals missing, material cleaved out of them. They held up pretty darn well. They weathered rock strikes, lots of riding, lots of abuse. I didn't treat these any different, like I said. Still use them on my bikes to this day, ride them all the time. And overall, in general, I really think these pedals are great. They really exceeded my expectations. They're strong, they're lightweight, they're really comfortable, they're customizable, which is really cool. Actually, a few of my friends are riding these too now. Few other, like for example, some other employees of Quest, when I designed these, were riding these around, and they're a lot of fun. They all really liked them. Now, if I can make bike pedals with these fairly easily, in a relatively demanding application, imagine what you can do at your company with technology this capable, especially manufacturing technology this capable, this fast, this flexible. It's something I'm really passionate about, and I'm definitely excited to be a part of this industry. That being said, if you didn't already see the design guide in the handout section, there's a QR code on the screen now that'll take you to the composites design guide. The Markforged website, specifically their Learn section you see on screen here, is a phenomenal resource. They have a lot of stuff that's not in the design guide, a lot of especially like post-processing and applications and design-related tips. If you're interested in really taking your design for additive manufacturing skills to the next level, reach out to us about Markforged University. It's a in-depth training class that you can actually get certified in. That goes over design for additive manufacturing and a few other aspects of additive applications, specifically in regards to like application economics, like part selection, etc. And this is a really awesome training course if you really want to take your skills to the next level. In addition, for more useful tips and tricks, reach out and check out our YouTube channel. There's the link on the screen there, and additionally another QR code. If you can't tell, I'm a pretty big fan of these. There's a lot of good stuff and a lot of good content on this YouTube channel. And then if you're interested in connecting with me personally, that is my LinkedIn profile address, and there's a QR code that will lead you directly to my LinkedIn profile. Thank you guys so much for coming to my presentation. Really enjoyed sharing this all with you. And if you have any questions, I will actually be answering some live right now. Turn on my webcam really fast. Where's the handout? So the handouts are actually going to be in the session information and documents and links. Approximate cost. Actually, I can go back and show you here. So pedals each are about $37 of raw material. Again, this is not a super economical project, but it is pretty cool that they're all custom. Switch back to this. Would a vapor smooth finish be a good post-production option? Yes. So we actually do offer vapor smoothing solutions at Hawk Ridge Systems. If I were to vapor smooth these, they'd be even more moisture resistant, and you probably wouldn't even be able to tell they were 3D printed. Actually, now I really want to do that. Scrolling through the chat and the questions here. If you guys have questions, feel free to drop those in the Q&A window. Okay, not seeing a whole lot of other questions coming through here, but I'll be around until about 9:50 if you guys do have questions. I'll start responding to some of your guys' chat. Someone's saying they fixed their ski boot with PETG. That's pretty cool. Yeah, if you're interested in it is really useful for that. Just to kind of remark on the material capability. A lot of these kind of other additive processes out there are getting to the point where you can kind of fix your own stuff if you have the right materials or kind of the right tools at your fingertips. Like this is a great example of something you can kind of do on your own. But I've done a lot of other small projects, as have our customers. I'm seeing from the chat. Someone's asking to see a 3D printed bike frame or forks. There are companies doing that. I would love to be a part of that. Could you select specific holes to reinforce per layer? That's a great question. So unfortunately, you cannot at this time. I'll actually jump back into Eiger and kind of show you what this looks like. So if I go into the 2D view, I can't specifically select specific holes. In this case, these holes don't really need to be reinforced in here, but I'm going to turn on reinforcement anyways. I'm going to turn on use fiber. And then what I'm going to do is I'm going to turn on concentric fiber. This is as close as you can probably get. And then say enter holes only. And then again, because these holes are pretty small, as you saw from the design guide, it's going to be a little bit of a challenge to get fiber around these because there's a minimum fiber length you have to extrude. And sometimes it's a challenge to wrap that around. If we change this to 3, we might be able to get it. But this is the closest you're going to get to being able to get inner holes reinforced or choose that as of now, at least. Okay. Well, awesome. It looks like we are getting close to the end here. It doesn't look like there's there's another question. How large of a chamfer can be added near the print bed using the 45-degree rule? This is in the design guide, but it kind of depends. The size of the chamfer, theoretically, and this is not trying to kind of break this out into a couple areas, but can be a couple, like it's really any size you want. But in terms of reducing like splay and like that warping you would see, or that like kind of swelling you'd see on the first layer, 0.5 millimeter to 1 millimeter by 45 degrees is would be a good starting place. I typically go with about 0.5 millimeter. But yeah, looks like we are got some good chat activity going on here. Looks like we're getting to the end here. Just to kind of shout out some things here again, thank you for Markforged for sponsoring this session. If you guys are interested in learning more, definitely check out the Markforged booth. I'll be around as well if you want to get in contact with me or talk to me at all. Don't forget to go to some of the other 3D printing sessions. We're going to be talking about blacksmith a little bit later today. My moderator, Jesse, is going to be doing that presentation, as well as a session on vapor smoothing later today as well. If you're interested in learning more about that, it just produces absolutely stunning parts. And don't forget to come to see the design print ride presentation. That was involved in that as well, where we actually fully we scanned a pair of snowboard bindings to get some boot interface geometry, designed them, printed them, and tested them. It's going to be really, really exciting to see if you guys haven't already seen that. With that being said, oh wow, seeing some other interesting, getting distracted by the chat. Todd, that's a really cool phone mount. Seeing that in the chat. I'm going to go ahead and end the broadcast, but I hope you guys all have a great day.